Hello everyone. This video is another video on numerical methods to solve equations. In the last one we went through the iterative process. This video is going to concern the Newton-Raphson process, which is another method for solving equations numerically. It refers the book on page 282. This is section 10.3, the Newton-Raphson method, also known as the Newton-Raphson process or procedure. And we have a formula, a recurrence formula, which is this. So we'll go through how this formula is derived, and then I'll do a problem where we use it. Okay, now okay, so here we've got an equation, or a function, f of x is a half x to the power 4 plus x minus 4, and we wish to solve the equation f of x equals 0. So this is the curve, and you can see there are two solutions, and we're going to investigate this solution here, which is between 1 and 2. We're going to try and find an approximation for that solution. It's a quartic, so we can't easily solve it analytically. Okay, and what the method involves is, like the previous time, we're gonna start with an approximation, a value which is close to the root there, and we're gonna, let's say we take 3, about there, and we're gonna go to that point on the curve, and what we're going to do is draw a tangent at that point. Here's the tangent, and as we can see, where the tangent cuts the x-axis there, if that value is a better or closer value to the root here than 3 where we started. So then we take that value, go to the curve and draw the tangent to the curve, and then we get the next approximation, and we can carry on like in that way. That goes to the curve, get the next approximation, go to the curve, draw the tangent again. Difficult perhaps to, there you go, and then you get, and we start getting very close to the root quite quickly. Here are all the new points on the curve. Here are the approximations. The next one you can see is around about 2.3. We get to 1.8, 1.6. Here we have all the values. I started around about 3, about 2.3, and so on. And you can see it very quickly converges to a value, which is an approximation to the root. So here we have in blue a function, y equals a function of x, f of x, and we can see we have a root here, alpha, and we're going to choose our first approximation in green here, and we're going to call the first approximation x0. Well, it's the not the starting point, x0. So we go up to the curve, we draw a tangent to the curve, and the first approximation then after that is x1. We can then go up to the curve again and then get a better approximation, but what we're going to do here is find the formula. What is the value for x1? Well, the tangent, the gradient of the curve is the gradient of the tangent. So the gradient of the tangent, f dashed, at that point where x is x0, is f dashed of x0, and that is the gradient of that line, which is the difference of the y coordinates, which is just f of x0 there, divided by the difference in the x coordinates, which we can see is x0 minus x1. So rearranging that formula, x0 minus x1 equals f of x0 over f dashed of x0, and so x1 is x0 minus f of x0 over f dashed of x0 x0. Properly x0 there. And then when we go to the next approximation, so we go to this point here, we draw a tangent at that point there, and then the next one is x2, and we'll do the same thing. So we will get x2 is x1 minus f of x1 over f dash of x1. And so this gives you a recurrence relationship, x n plus 1, the next one would be xn minus f of xn over f dash of xn, the derivative at xn. Okay, so now what we'll do is we'll use the formula to find these values here that we've got on this graphical calculator on GeoGebra. So we're going to calculate these values. So the function is a half x to the power of 4 plus x minus 4. And using the formula we have to get f dashed of x. So we need to differentiate, and simple derivative here, f dashed of x would be 4 times a half, 2x to the x cubed plus 1. So the formula becomes x to the n plus 1 is equal to, and then it'll be 0.5 times x to the n to the power of 4 plus x to the n minus 4 over 2 x to the n cubed plus 1. Okay, so our starting point x0 was equal to 3. So x1, the first approximation, going to be a half times 3 to the power of 4, which is 81, minus 3. Oh, is that minus? I think that should be plus x to the n there. So plus 3 minus 4. Oops, made a mistake there. I meant to write 3 minus, if you can see the formula, it's x to the n minus f, so 0.5 3 to the power of 4, which is 81, plus 3 minus 4, plus 3 minus 4, over 2 times 3 cubed, 27, plus 1. And if you work that out, that would come to 2.2818. Okay, I'm going to show you how to use a calculator to get the subsequent approximations very quickly. It's similar to what I was doing in the iterative process, because this is another type of iterative process. See in the calculator here, I've put in basically the formula, the Newton-Raphson formula for this case. And if we press equals, there you go. That is the answer. I'll put it in decimal form. It looks like that. 2.28181818. That is the first approximation. Well, I'm going to call that the answer. So to get the next one, I'll put the formula in with that as the answer. So we start off as x1, which is that value, which is the answer. So that would be answer there. And then I want to go minus, and I have that fraction, so put in the fraction, like that. And then it's 0.5 times the answer to the power of 4, and then move down, plus the answer, minus 4, move down to the denominator, and we want 2 times the answer cubed, so it's shift there, cubed, and plus 1. So now if I press equals, here 1.80379, that's the next approximation. And then to get the third approximation, press equals again. It replaces the value there in the answer as the answer in the formula, and so you get the next approximation. 1.56 there, 1.5499. If we go going a few approximations, you see I keep pressing equals now and it doesn't change. So we get into the to the root quite quickly there. And here down here were the values that we had when we used GeoGebra. You can see that in this case, very quickly, it was we were getting to correct to 10 decimal places after very few iterations. It doesn't always happen so quickly. It does rely on the tangent being quite steep and being closer to the solution. So you have to choose your first approximation very, very carefully. Here is an example. If you choose, here's a root which is close to a minimum. Choosing this value over here, because we've got a gentle slope for the tangent. This is the root. If we choose this value, near close to a minimum, then the tangent is very gentle, and we can see that the next approximation is further away from the first approximation. So this will either not work, it will diverge, or maybe will go very slowly to the root. And it is, if you chose the minimum point itself, that wouldn't work at all, because the value of the gradient here is 0, so you'll be dividing by 0 in the formula. Right, so that's the Newton-Raphson method. If we go to the next page, page 284 in the book, you can see exercise 10C, and I suggest that you practice doing that, and I shall set you another question to do for homework.